So basically what we've done is we've replaced this entire thing that has a sequential dependence chain with this, which is hopefully much, much simpler. I guess I don't have the slide. How do you assign the, okay, I'll describe it over here. Basically, how do you pick the golden flit? This is actually relatively easy now. Basically, you need to somehow ensure that there are two conditions, right? First, each flit needs to be picked. Second, a flit needs to be prioritized until it arrives at its destination. And I think third, all routers need to pick that flit, right? So a very simple scheme is you have potential containers for every possible packet, right? You can, for example, every possible node, you have node n and potential flit m. Let's say n, a total of n by m potential flits that you can have. You basically cycle around this. Let's say, and you determine this first. This is, you have potentially n times m flit slots that can ever be present at any given point in time. And the second thing is, you need to determine how long it takes to deliver a flit to its destination. And you need to find the maximum latency of that within that network.
That's from source to destination.
Source to destination, exactly. Assuming it's prioritized, right? From source to destination. Assuming it's prioritized, of course. Right? So, and you can figure this out for any network. For mesh, it's easy. And you don't need to, you just need to consider the network. You don't need to consider the memory latency, right? Because once the memory responds, you do the same thing again. So assuming that you've figured out, basically every router has this knowledge, and every router starts a time-based prioritization scheme, saying that, let's assume that this is L cycles. For 0 through L minus 1 cycles, the router says node 0, flit 0 is prioritized. For L to L minus 1 cycles, every router says node 0, flit slot 1 is prioritized. And you keep doing that. You keep cycling that. Now, if a router sees during this time this flit, it says, oh, this is the golden flit, and prioritizes that. It may be that there may be no flit associated with this potential flit slot, right? In that case, we're basically not having a golden flit in any place in the network, but that's okay, right? Eventually, any flit can get to its slot and will be prioritized. And this is the simplest possible mechanism that you can potentially build, I think. And it turns out we don't see many flits becoming golden, because this is, again, live lock is not a common case. It's a very, very uncommon case. So we don't see many flits becoming golden, so we don't see this prioritization to become a big issue, at least in our workloads.
In case of a real-time environment, we probably will inject more into the for individual flits, right?
That's right, yes. Yeah, basically, you still have a deterministic guarantee as to when, but that deterministic guarantee may be very long, right? You basically, a flit in the worst case will become the golden flit after n times m times l cycles, right? Which could be pretty large for a large network. So worst case guarantee is bad here. But you get a guarantee, you get a deterministic guarantee. You can have probabilistic guarantees also, but then you may lose the live lock freedom, deterministic live lock freedom. We've looked at probabilistic guarantees too, but that's interesting too. Okay, so let's take a look at the other issue, which is packet reassembly. So reassembly buffers are large because in the worst case, every node can send a packet to one receiver. So if this is the receiver, every node can have a packet sent here. As a result, you have ON space. So why can't we make these reassembly buffers smaller? Let's assume that reassembly buffers are actually small. There are 2 entries here, and you have many senders. In this case, let's say the reassembly buffers are allocated to these, and these are the packets, and they're waiting for their corresponding flits so that they can be ejected into the node. And only 2 of these packets are actually buffered. Now the nodes can keep injecting packets, right? This is a different color. Unfortunately here color coding doesn't work well. But this is a different yellow than this yellow. So the network cannot put this packet or flit into the reassembly buffer because the reassembly buffer is full. Now as a result of this, let's say lots of things are injected, eventually network can become full. And we cannot inject new traffic over here, but we have to be able to inject this packet, which matches this, by the way, to enable an entry in the reassembly buffer. And we have to be able to inject this packet, which matches this one, to enable that entry. But we cannot inject these, which means that we cannot deallocate the reassembly buffers. And at the same time, network becomes full, which means that we have a deadlock, right? Because the reassembly buffers are full.
What we're doing here is having those flits being alive. You're saving buffers at the intermediate nodes, but kind of you're shifting the problem to the destination nodes, which all of them may be some kind of destination node.
That's right.
So this is distributed all over the nodes, the buffer requirement. I mean, if a flit arrives, just to wait for the other flits, which their arrival will be rather late because you're deflecting and they're going around and around before you arrive. So there will be not so well utilization of the destination buffers for reassemble, kind of. Is that true?
So we're going to get rid of this problem. Yes, you're right. So we're shifting the problem to the destination.
At the destination node?
Yes, we're deflecting them at the destination node also. Yeah, so if for example, this cannot eject, we're going to send it back. And it'll circle around in the network until a destination buffer is available. You can make it more complicated, but that becomes complicated, I think. You can say, okay, I'm going to eject this one and inject something else into the reassemble buffer. So you can swap. That's right. So these things become a problem. That's right. These things become a problem when you have lots of load on the network. These are normally not problems, but you need to ensure that the network operates at high load also. But you're right, we're shifting the problem here, and we're trying to solve this problem now. Okay, so yeah, how can we solve this deadlock problem? So basically, one solution is actually, people have looked at these solutions in different ways. You can reserve space to avoid deadlock, right? That's a very conservative solution. You can say every sender asks permission from the receiver before it sends. Not a good idea, because that's very conservative. So this sender, it's going to send these 2 packets. It first asks, do you have a reassembly buffer? And the receiver says yes, and it reserves the buffer, and it acknowledges, and then the sender can now send nicely. It adds additional delay to every request. So we don't want that.
Additional wiring also.
That's right. Well, you could still use the existing network, additional congestion on the network, yes. You can do retransmissions. On the other end of the spectrum, you could always say, I'm going to assume the buffer is free and I'm going to always transmit. If that's not true, the receiver drops and sends a NAC, negative acknowledgement, and sender retransmit in that case. So in this case, protocol is a little bit more complex, but sender always sends the flits, and it gets dropped if the reassembly buffer is full. In that case, the receiver NACs, saying that I've dropped your flit, send it back. In the meantime, some other packet completes, and if the sender is lucky, a reassembly buffer is available, and then the receiver acts, and the sender can now deallocate its buffers. So the upside is there's no additional delay in the best case, and transmit buffering overhead for all packets, so you need this overhead. Although in many core networks, actually this exists. So in a cache, for example, you actually have these buffers. Whenever you take out a cache line, you keep it somewhere. So this is not a big deal in the many core on-chip network. In a general network, this may be a big deal. And potentially there are many retransmits, right? If the network is congested, this is actually a bad idea again, because everybody keeps retransmitting and you have this congestion problem because of retransmit. So the solution that we've come up with is retransmitting only once. Basically the key idea is to retransmit only when space becomes available. receiver drops the packet if the reassembly buffer is full, and it notes which packet it drops. And when a buffer becomes available, it tells the sender that now you can send the packet. At that point, it reserves space. That's the idea. And receiver notifies sender to retransmit, basically. So if you look at the protocol, it's a little bit simpler now. The sender initially says, I'm going to send the packet. The receiver drops the packet and basically makes a note saying that node 0 request 0's packet was dropped. And it can actually, basically, you need to have a buffer to keep track of this. Actually, it's really a bit vector. So it's not that bad. The buffer here is not that bad. It's very similar to this n by m, actually. It's n by m bit vector. That's all you need. And when the receiver, when some buffer becomes free, the receiver takes the top pending request and says, reserves the request for node 0 and tells node 0, I dropped your thing, so can you send it to me again? And node 0 sends the packets now. This is the retransmit once. So you only have a single retransmit that happens here, and that doesn't congest the network. And you ensure that deadlock freedom is satisfied. So now, actually, you can do one more optimization. It turns out in many core networks, this buffer doesn't need to be separate from the cache buffer. So you can really use, whenever you request, so when you actually need to get multiple flits, you usually get different parts of the cache block, right? So normally, you have a miss buffer that is allocated for that particular cache block in the cache, right? This is called the fill victim buffer or miss buffer or load store queue if you actually get too close to the processor. But that can be used as the reassembly buffer itself. And that is actually already organized to receive parts of the cache block. So you can actually get rid of reassembly buffers and make them the same as miss buffers with some additional logic to handle this retransmission.
And maybe body sets, and they may have shared buffers, maybe. So that I mean, individual nodes may not have that much buffers, but local body sets may have some.
That's right.
To hold it local temporarily, then get it.
And then get it. That's right. Exactly. Yeah. Exactly. So you could combine the buffering. This doesn't need to be separate. So that way you can get a truly bufferless network because you use these additional buffers that already exist for a separate purpose. Okay, so what we've done is basically in the baseline bufferless deflection router, we had this complicated deflection router logic. It had a long critical path. It sorted by age and it allocated ports sequentially. We got rid of this with the golden packet and the permutation network. And reassembly buffers, baseline bufferless network needed large buffers for worst case. So we changed that with retransmit buffers and we used cache buffers, miss buffers, to eliminate the need for reassembly buffers. So in the end, the router we have looks like this. You still need to have some injection logic, but that doesn't have to be as much on the critical path, but that's one cycle. And you also need to have this permutation network. And you inject and eject into the miss buffers. So let's evaluate this a little bit. We've looked at a lot more workloads in this later work, and some multi-threaded workloads as well. And these are the configurations of the baselines. Again, we look at perfect L2 so that we can stress the interconnect. Whenever you make the L2 real, many workloads start missing. Missing in the cache. As a result, interconnect becomes less of a bottleneck. That's why I think energy efficient interconnect becomes much more interesting going forward. You still need the interconnect for those workloads that actually need it. But for those workloads that don't need it, and for when you don't need it, it needs to be very energy efficient. So we have Verilog models of all of these and some power simulation. So let's take a look at the performance degradation first. This is a more realistic evaluation. So this is, I think, for 8x8 network, 64. This is a very extreme case. These are very bandwidth intensive applications. Every node is running extremely bandwidth intensive applications. As a result, over there, the performance degradation is pretty high when you actually go from buffer to bless, which is our previous work, and chipper, which is this better router. And you do get performance degradation because of chipper, because now you get a lot more deflections, right? Because you don't have this total order. And this is the performance degradation. It's about 13.6% compared to bufferless network. In multi-thread workloads, it turns out these workloads actually do not stress the interconnect that well. Maybe they're not representative workloads. So most of the workloads fall into this category. The performance degradation over there is low. But there are some workloads, if you construct this worst case, every workload is running the stream benchmark, for example, the network is congested significantly. So there's minimal loss for low to medium intensity workloads, but for high intensity workloads, there's high loss. Power reduction, on the other hand, is high. It's 55% from the buffered network, and Chipper actually reduces the power consumption over the earlier buffered router because of the reason you said. Basically, if the buffered router critical path is long, you consume a lot more power because of that logic. And there's even more reduction in multi-thread workloads. This is network power only, it's not the system power. So you can reduce the network power significantly. What about the critical path? So this is, first of all, this is the router area in a buffered router. If you normalize to the buffer router, we can reduce the router area by 36%. And this again through RTL models with optimized buffers. And the critical path, we actually save area compared to BLES also because that logic to do the sorting has higher area. If you look at this, we reduce the critical path compared to BLES by 29%, and our critical path is within 1.5% of the buffered router. So it's not as bad as before. Okay. So conclusions, there were two key issues in bufferless deflection routing. One is live lock freedom, and the second is packet reassembly. And they were high complexity and impractical because we didn't solve these problems in that original paper. But I think we've solved the problems now. We have oldest first prioritization led to long critical path in the router, and there was no end-to-end flow control for reassembly. As a result, the network was prone to deadlock with reasonably sized reassembly buffers. Chipper is a more practical bufferless deflection router. Because of golden packet prioritization, you get short critical path in the router. And because of retransmit once protocol, you get deadlock-free packet reassembly. And using the MIS buffers as reassembly buffers leads to a truly bufferless network. And you get a router with a frequency that's comparable to buffered routers at much lower area and power cost. And hopefully with minimal performance loss. Yes?
You're assuming your NACs are never lost, so they are somehow prioritized in the network to not be dropped or deflected, or are they following the same logic going forward?
Yeah, they're following the same logic. They will eventually get delivered.
So they can be delayed?
They can be delayed, yes. That's right. But you can actually prioritize them, make the router a little bit more complicated and prioritize the NAC. But we didn't do that for these results. And that's part of the where the performance degradation is coming from, you're right.
But we're not looking at delay per se. This delay is not a parameter that we are looking at. We're just looking at
overall performance, yes. We're not looking at the packet delay, you're right. Okay, do we have more time? No. Any other questions? Okay, so actually I don't think truly bufferless networks are the solution. So I'll describe to you adding a little bit more buffering into the network. And this is a much more interesting solution, I think. We call this a minimally buffered deflection router. And this is my student Chris Fallon's work. Again, if you look at deflection routing, it's good. It has a lot of upsides. But at high network utilization, you get a lot of unnecessary link and router traversals. You keep deflecting these packets all over the place. This reduces network throughput and application performance. It also increases dynamic power. So this is our goal in this work. We're going to improve high load performance. Yes?
What's the intuition in why does buffer consume so much power?
Why does it? First of all, it consumes static power because even when it's sitting there, it's just leaking. This will become even more interesting when we talk about the next lectures, but it's leaking energy. The second is it consumes dynamic power. You need to read and write from and into the buffer, and that consumes a lot of energy. And the third thing is you need to manage the buffers, right? You need to do flow control. You need to say this buffer is empty or this buffer has this much utilization, and you need to transmit that information to the previous router saying that don't send me a packet, right? Whereas with bufferless routing, you don't need that fine-grained flow control. You need to have end-to-end flow control, but not local flow control. Those are 3 reasons.
Just keeping the bit pattern the way it is for longer periods of time.
That's right, yes. You could gate the power. You could use a lot of the other techniques. So these actually assume a lot of clock gating and not using the buffers. Even power gating we assumed in many of these results. But even then, the buffers consume power. And this is also repeated in many studies. I think people have looked at that. That's it. That's the interesting part. You can optimize the buffers. That comes at additional complexity of the design. You could make it very low power, but still you cannot get rid of the fundamental energy consumption. Okay, so basically we would like to, well, what do I mean by high load performance? This is basically that, remember the load delay curve. If you look at this is a buffered router, and this is a bufferless, well, maybe it's not that good. This is a bufferless router. There are some workloads that fall here. Maybe they're not the majority, but they're there. Or there are some workloads that fall here, maybe not that high. Basically, bufferless routers are pretty bad for the class of workloads that fall here. So we'd like to improve the high load performance. We'd like to add a little bit of buffering to get the performance of those workloads that seem to fall here. So how do we do that? I think I can skip the background. Basically, we talked about correctness. So Chipper actually enabled a lot of correctness. It did improve performance, but our main goal was correctness. But now we're going to try to improve performance. And what performance degradation at high load? So there's several performance issues. One is link contention. Because there are no buffers to hold traffic, any link contention causes a deflection. Whenever 2 packets need to go to the same output port, you have a deflection. We want to get rid of that. The second is we've actually found that ejection becomes a bottleneck in the bufferless network. You can have only 1 flit ejected per router per cycle. If you do that, whenever you have a simultaneous arrival, you get a deflection. You cannot eject both packets at the same time. As a result, you consume a lot of power because that packet needs to go back and come back again. And if you run into a situation at the high load, all packets arrive, and they all need to go back, well, except for 1, and they come back again, and they try again, and one of them only makes it, and some of them need to go back and come back again. So you can see that this is a bad thing to happen, right? And finally, practical deflection arbiters deflect unnecessarily. So in the Chipper work, we were randomly picking the flits. But maybe you want to have some priorities, right? If you add some priorities, you actually reduce the deflections. And this is actually an interesting balance because as you add more priority, saying that your router should pick 1 flit and prioritize it, it becomes a more complicated router. But you do reduce the deflections because now you're actually ensuring that the flit goes to its destination. Before we were ensuring only the golden flit goes to its destination, right? Which is guaranteeing live lock freedom, but it's not good for performance. So we'll take a look at all of them. So to solve the link contention issue, we're going to use side buffers, very limited form of buffering. And to reduce ejection bottleneck, we're going to eject more than 1 flit. I don't think there's another way of solving this problem. So it doesn't sound that great, but we'll have to do it. And to reduce deflection arbitration, we're going to have more priorities, basically.
Flit per port? That is 2 flits per port? Or 1 flit?
No.
So you assume there are 2 ports?
2 ports, yes. We're going to assume there are 2 ports, basically, yes. You can overclock the port also, but that becomes...
What was your assumption at the beginning? Because you assumed that your output ports are more than your input ports. Why not? It's the initial assumption.
That's true, but there's only 1 local output port. No, we assumed equal actually for the mesh, but there's only 1 local. If 2 things need to go to the local output port, one of them needs to be deflected. Okay, so we're going to add more priorities basically. You don't need to have a golden flit, you can have a silver and bronze flit too, right? And you can keep that, increasing that. As you increase that, you run into a trade-off, of course. Let's take a look at these very quickly. So any link contention causes a deflection. Buffering a flit can avoid deflection on contention. But if you do buffering as usual, as virtual channel buffered today, buffered routers do, this is not a good idea, I think, because all flits are buffered on every hop, at least high dynamic energy, and large buffers are necessary. You get high static energy in large area. So we're going to add a small buffer to a deflection router to buffer only those flits that would have been deflected. And we're going to limit its size. So basically, this is our baseline bufferless router. Let's say these 2 flits need to go to their destination. Basically, one of them gets deflected because they happen to have their destination over here. So we're going to fix this problem by having a side buffer, make the router a little bit more complicated, and we're going to re-inject that flit over here. These 2 flits, they need to go to that destination. One of them gets deflected, the other takes its destination, it moves, and the router takes the deflected flit, removes up to 1 deflected flit per cycle from the outputs, and places it into a small FIFO side buffer. And that side buffer re-injects this flit into the pipeline when a slot is available. So you have a circular path here. Of course, you need to ensure that these flits are re-injected. So we have a mechanism to ensure that there is no deadlock in this case also, right? Because if this flit sits there for a long time, there's a problem, starvation problem. And you can read the paper for that. So that's the idea. In the second turn, hopefully it gets its destination. If it doesn't, it'll wait and it'll keep trying again. Okay, so why could a side buffer work well? We're buffering some flits and deflecting other flits at per flit level, right? So relative to bufferless router, the deflection rate actually reduces because you need not deflect all contending flits. Right? So if you have a 4-flit buffer, deflection rate reduces by 39%. And as you increase it, you get diminishing returns. So relative to buffered routers, this buffer is more efficiently used because you do not need to buffer all flits. Right? We're buffering only some flits here. And we get similar performance within 25% of the buffer space. So you can reduce the buffer space significantly. And it's a simpler buffer to manage because you don't have lots of them. Okay, so how do we, this is a simpler one. Basically, we do not want to have this unnecessary ejections. And we found that actually in 20% of all the ejections, greater than or equal to 2 flits could have ejected at that time. All but 1 flit must deflect and try again. And these deflected flits could cause additional contention. So if you actually reduce the, increase the ejection width to 2 flits per cycle, you reduce the deflection rate significantly. And that's the idea. This is simple, right? So how do you do that? This also complicates the router. We're going to add another port basically. Before we were ejecting this way. And this, even though the goal was to get to the local port, it needed to go through the router, and it got deflected, and it comes back later on somehow, and then it enters ejection. But now we're going to add 2 ejection ports, so you could do this in parallel even. Okay, so this will actually increase the complexity of the router, right? Because we're adding more stuff to the router. So for fair comparison, baseline routers have dual width ejection also, and they actually benefit from this also, interestingly. But we do not penalize, this is also important, we do not penalize the baseline routers for the power and area for fair comparison. Basically, we give them the benefit of the doubt for the performance, but we do not say charge them for the power or area of this additional ejection port. Okay, so the last thing is how do you actually improve the arbitration? If you have age-based priorities, we've seen that you get fewer deflections but require slow arbiters. So this is the full priority scheme. Right? You can have a priority with each flit. But before, we've seen golden packet and a 2-stage permutation network. We prioritize only 1 packet globally, not locally, but globally only 1 packet is selected to be prioritized. Everything else is randomly arbitrated, right? So this is a bad idea. This is a good idea for a fast critical path, but a bad idea for deflections because you randomly pick a packet and you may deflect every packet. And I'll show you an example. So you basically get uncoordinated arbitration. Let's take a look at that. Well, we've seen this, right? You have this building block that picks a winning flit. If that winning flit is a golden flit or golden packet, then you pick that one. Otherwise, you randomly pick one of them. And again, highest priority flit always route to the destination. You steer the winning flit to its desired output and deflect the other flit. Let's take a look at a case where lots of flits are deflected. Each block makes its decision independently, right? So all flits, no flit is golden, let's say, and you have pseudo-random arbitration here. This flit needs to go to its destination, which is at the top. and this flit needs to go to its destination, which is here. Now what might happen is red flit, which is this one, wins at the first stage here. And it goes this way. You randomly pick, right? And blue flit loses, it goes this way. And then green flit loses, green is this one, at its first stage, which means that it goes that way. So it's already deflected, right? It cannot go to its destination. And this, I think it's not yellow, but yellow flit goes this way, has to go that way. So now, in the second stage, because we do not have any priority, this router can randomly pick this one, right? To be the winning flit. And red flit loses, so you get an unnecessary deflection here. And here, everything is deflected, basically, which is not what you want. So by adding more priorities, you can reduce the deflections. And that's the idea here. Add one priority level. We've actually looked at other priority levels, but there's a trade-off between router complexity and performance. Basically, the idea is add a priority level and prioritize one flit to ensure at least one flit is not deflected in each cycle. So highest priority is still one golden packet in the network. It's chosen in the static schedule that I described here. This ensures correctness. So next highest priority is one silver flit per router per cycle. It's chosen every cycle by the router that sees the flits. It chooses it pseudo-randomly. And this is the goal is enhanced performance here. So basically, if you look at the previous example, all flits have equal priority. We've changed that to a red flit has higher priority. Randomly, red flit becomes silver. In this case, red flit definitely wins at the first stage because it's silver. And this is deflected. And green flit is deflected in the first stage because it's pseudo-random here. Red flit, again, definitely wins in the second stage because it's silver. So now it goes to its destination. So at least it's not deflected in this case. So that's the idea. You could add more priority levels, obviously, right? You could actually have another priority level here that potentially allows this one to win. But now that becomes more complex, right? Okay. And we didn't see that much benefit from it. So this is the final router. Basically, the side buffer solves the problem of link contention. This dual ejection solves the problem of the ejection bottleneck. And we basically have a two-level priority scheme to reduce unnecessary deflections. Let's take a look at what actually this results in. We've actually improved the simulation methodology significantly in this final work. So these are more reliable results, I think. Well, you can read the paper. We have more workloads also. And these are the different comparison points that we have. These are buffered routers. And we've actually swept over a large spectrum of router designs. And bufferless deflection router and a hybrid router. People have proposed switching between buffered and bufferless routing at a coarse grain level. This is a more complicated router because it has both buffers and deflection routing logic. Basically, at low load, the idea is at low load, you disable all the buffers, you power gate them perhaps, and you switch to bufferless routing, just like we described in Bless. And at high load, with a threshold, you switch to buffered routing. So the router is more complex here, obviously, because it needs to support multiple different ways of doing things, but the purpose is to save energy. And these are some common parameters. So we actually have better models and some power models. So let's take a look at the deflection rates of these different mechanisms. So this is the baseline bufferless chipper router. And this is the effect that you get in terms of performance averaged across all workloads as you add a side buffer, as you do dual ejection, and as you had silver flits. And as you combine all of those, and we have actually more, but they're not shown here. You have pairwise combination. But this is the final router. If you look at the final deflection rate is 28% of all flits are deflected in the baseline. Adding a side buffer reduces the deflection rate, but reduces performance also, actually, because now you have additional complexity. And you can do dual ejection. It reduces deflection rate, increases performance. And silver flits actually doesn't reduce deflection rate significantly unless they're combined with these other mechanisms. Well, side buffer alone is not sufficient because the ejection bottleneck remains. Actually, it turns out side buffer makes the ejection bottleneck higher. You can read the paper for more detail. So when you add min BD, we can actually raise deflection rate to 10% from 28%. So overall performance gain is 5.8% over the baseline, and 2.7%. Baseline is the bufferless deflection router, I think, if I remember correctly, but maybe I don't remember correctly. It should be the bufferless deflection router, yeah. 2.7% over the dual ejection, and you can reduce the deflection that way by more than 50%. So these are the overall performance results that includes the buffered routers as well. Now, and also this coarse grain switching between buffered and buffered. If you, the performance improvement still exists over chipper, it's 2.7%. So we bridge the gap between bufferless and buffered. And the performance improvement is high when the load is high. And it's within 2.7% of buffer. So you can bridge the performance gap by half between buffered and bufferless. And that's true for the high load also. Basically, you get performance similar to this buffered network at 25% of the buffering space. So some power results, I'll not go through this in detail, but this is actually a very detailed power model. And you can see the different powers. And this is the non-buffer power dominates with min BD. Buffer power is very, very minimal. And this is the baseline buffered routers. Okay. And this is the dynamic and static power. You can take a look at that. Okay, lots of results. So this is an interesting graph, I think. This is the performance and power spectrum. This is the network power here. And this is the performance of different routers over here. And these are all different kinds of buffered router designs. And we've picked out some of them. Buffered router with 8 virtual channels and 8 flits per virtual channel is here. So its performance is very high, but its performance is very high here. It's not that much higher than some of these buffered routers, but its power is very high also. I think chipper is here. Its performance is relatively low, and power is also low. Not as low as buffered, but this is actually a bad buffered design because you actually underutilize your links by having one buffers because you don't even cover the round trip latency of transfer. So if you look at this, min BD is actually at the Pareto optimal curve for energy efficiency. It's basically, it has more performance and power over here if you draw that curve. And I don't think the paper should have variations on the size of the buffer for min BD also. Okay, what about the die area and critical path? We've actually made the trade-off of increasing the die area and critical path a little bit compared to chipper. So there's 3% area increase over chipper, but the area reduction over buffered network with 4 virtual channels and 4 flits per virtual channel is still significant. And critical path increases a little bit, unfortunately, compared to chipper. And that increases about 7% and 8% compared to the buffered baseline. But this may not be that bad. It depends on the frequency you're going to run the network at. Right? Maybe 8% is not too bad compared to buffered. Okay, so I think I've shown that bufferless deflection routing offers reduced power and area, but high deflection rate of the packets hurts performance at high load. We've designed a minimally buffered deflection router that introduced a side buffer to hold only flits that would have been deflected, multiple with ejection, and 2-level prioritization to avoid unnecessary deflections. Actually, multiple with ejection can be seen as avoiding unnecessary deflections also, right? Because you're avoiding unnecessary deflections at the destination. This yields reduced power and reduced area relative to buffered routers. And it yields improved performance relative to buffered routers, closes half of the performance gap between buffered and bufferless. And it has the best energy efficiency of all evaluate designs at competitive frequencies. Okay, I can keep going and we can cover many, many more things. But maybe, what do you prefer? It's already 9:06 a.m.
No problem, we can go to 50.
Oh, really?
If other people are also willing.
What do people think? Any questions so far on this? I have a lot more material for 4 more hours probably, but I don't want to go for 4 more hours. maybe I can describe a little bit more if anybody can leave, of course. Sure, yeah, that's right. It's already, I think, 5. Yeah. Okay, maybe I'll go a little bit more and then we can stop. Maybe I'll finish the bufferless part. There's a lot more actually. This is a very exciting area. But again, there are some readings. If you're interested in the studies of congestion and congestion control in on-chip and internet-like networks, I'm not going to talk about this paper. I'm going to talk about some other paper that actually provides a better mechanism, but that doesn't talk about on-chip versus internet-like networks. There are differences. I'd recommend this paper that was published last year at SIGCOMM. SIGCOMM is a networking conference, not a on-chip. Actually, you can ask me how hard it is to publish a on-chip networks paper at SIGCOMM. People tend to be very
very internet types.
That's right. Yeah, they don't want to know about other things in the world. Maybe. Okay. So I'll talk about another way of improving performance, and this is heterogeneous adaptive throttling. And this is another way of improving performance, especially if you have multi-programmed workloads, if you have different applications. And this should be very quick. The problem is we have packet contention on chip networks, which causes congestion and reducing performance. We've observed that some applications are more sensitive to network latency than others, and you can discover this dynamically. And we also observed that applications must be throttled differently to achieve peak performance. Throttled meaning they should be prevented from injecting into the network. Because if the network is very highly loaded, if you're here, if your network can support this much injection rate, and if you're operating here, that's too bad. One idea is to actually reduce your injection rate, throttle the applications, and operate at this level such that your latencies, applications are actually making faster progress. Operating at this level is a better idea. Right? And that's the idea of congestion control. Reduce the injection rate so that you can get to a level that's not saturated. The new ideas here, people have looked at this a lot, of course, right? This is already employed in the internet with different mechanisms. But the new ideas over here are using application-aware source throttling. So if you have a many-core interconnect and that's running different applications, maybe you should be aware of those applications and adapt your throttling mechanism to that. And also to adjust the throttling rate based on the network load. And the result, I'll show you some results that show performance improvements and energy efficiency improvements over state-of-the-art source throttling policies. So we already talked about this, so I'm going to skip these. So when you get network congestion, there are two things that happen. Network throughput reduces, and basically throughput, how many packets you're servicing per cycle reduces, and application performance reduces. So these are all red packets that need to go there, and you cannot inject because you're congested over here, right, in that router. We're going to try to solve that problem. So reducing network load decreases network congestion and hence improves performance. We're going to use source throttling. There are many other techniques to reduce network load, right? You could do better application mapping to the network if you can do that. So you could move the application from one place to another. You could move communicating applications close to each other, right? But we're going to use source throttling in this case. We've actually looked at other application to core mapping policies also that I'm not going to describe here. And they do reduce the network load also. But basically the idea is to temporarily delay new traffic injection into the network. Naive mechanism that people have looked at a lot is to throttle every single node. But different applications actually respond differently to change the network latency. So this is two applications. This is not the most sophisticated example, but you have one network non-intensive application and one network intensive application. And we're looking at the performance of each of those applications and the performance of the system when one of them is throttled. If you throttle GROMACS, which is not network intensive, the performance of MCF doesn't change, performance of GROMACS doesn't change that much, and performance of the system doesn't change that much. In this case, if you throttle MCF, you gain significant performance benefits on GROMACS because MCF is network intensive and it's delaying this network non-intensive, more latency sensitive workload. You can think of this as bandwidth intensive and latency sensitive. So if you throttle only MCF, you can actually improve system performance significantly by just doing that simple optimization. because GROMACS is more sensitive to network latency. Now these are actually interesting applications. You can take a look at them. Okay, so basically throttling network intensive applications benefits performance a lot more. The second observation is, if you look at these workloads, this is the throttling rate. How much do you throttle an application when you need to throttle it? And this is the performance on the x-axis. Higher is better. Throttling rate, 100% throttling rate is basically you say the application doesn't inject into the network. 90% throttling rate means every 10 cycles out of 100 cycles the application can inject. Basically every cycle you flip a coin or you generate a random number. If it's greater than 0.9, let's say your random number is between 0 and 100. If the generated random number is greater than 90, you inject. Otherwise, you cannot inject. And if you look at these curves, this workload's performance saturates here, this workload's performance saturates here, and this workload's performance saturates here. And it turns out this is very difficult to determine. If you come up with an analytical model to figure out how to actually model this, this becomes very difficult. We've tried very hard to come up with analytical models that try to figure out where the performance saturates and how the performance saturates, but the system seems to be very chaotic to model very well. Or maybe we're not good enough to model it very well. That's another possibility, right? Always. So dynamically adjusting throttling rates, but I think the first part is the hard. I wouldn't suggest anyone to look at that problem. If you want to model a network to figure out this ideal throttling rate, especially with real applications, it's going to be very tough. With some traffic patterns, maybe you'll be able to do it, but with others, you cannot. I think it's going to be very tough. So dynamically adjusting throttling rate yields better performance than a single static rate. That's the key observation here. So how do we achieve both? I'll just give you the key ideas here. Basically, there are two key ideas. One is application-aware throttling, throttle network-intensive applications that interfere with network non-intensive applications, and dynamically adjust throttling rates of those throttled applications to adapt to different workloads. Let's take a look at the first one. Basically, how do you do this? First, we want to measure network intensity. Basically, we're going to use L1 miss rate per 1,000 instructions to estimate how intensive an application is. Basically, this is the injection rate of the application into the network, assuming that we have cache block traffic or cache miss traffic. Then we're going to classify the applications. Basically, we're going to sort the applications based on L1 misses per 1,000 instructions. And we're going to classify some of them as network non-intensive and some of them as network intensive. And that's, we have a cap that we're going to determine dynamically again. And we're going to throttle network intensive applications. These will be throttled at some rate, and we're going to determine that rate dynamically. That's the second part. So for a given network design, peak performance tends to occur at a fixed network load point. But this is also dependent on the application communication patterns. So we're going to dynamically adjust the throttling rate to achieve that network load point. We have a very simple mechanism. The idea is to maintain network load at a peak performance point. So we're going to measure the network load and compare and adjust the throttling rate to that peak point. If network load is greater than the peak point, we're going to increase the throttling rate. Else if the network load is less than the peak point, we're going to decrease the throttling rate. That's the idea. It's pretty simple, right? So this is an epoch-based mechanism. Basically, in the current epoch, in this case it was 100,000 cycles, we measure the injection rate into the network and we measure the network load. In the next epoch, beginning of the next epoch, the applications are classified. Somebody needs to do this. In hardware, there's a node that does this. It adjusts the throttling rate and it resets the measurements. So what did prior works do? Very briefly, this is our previous work. We've looked at throttling based on starvation rate, and it doesn't adaptively adjust the throttling rate, and it doesn't classify these applications in the way that we've discussed. It basically looks at the starvation rate, how much starved a node is, how much it cannot inject into the network. It turns out this is a better mechanism than the starvation rate. We call this a heterogeneous throttling. There were also works in throttling. This is one of the most recent works, throttling off-chip networks, off-chip interconnects. Basically, you can observe the buffer occupancy, and if the buffer occupancy is high, you can dynamically trigger throttling. That's the idea. The downside of these works is they're not application aware. They fully block packet injections of every node. That's the throttling mechanism they used. This is called self-tuned throttling. They're self-tuned because they try to find the point where the injection rate is very close to saturation throughput. But again, they're not aware of different applications. So let's take a look at some of these results very quickly. And I think people are getting tired, so this will be the last part that I'll cover. I'll leave the slides to you for the rest of the ideas. I think this is the most sophisticated simulator we have that has this on-chip network and everything else as well. So you can read about that. So what is the performance of this? Basically, the performance improvement over this heterogeneous throttling is about 7.4%. And that's our previous work. And the highest performance improvements are actually on heterogeneous workload mixes, which makes sense, right? Because you're throttling different kinds of applications. You get significant performance improvements because there's applications that are sensitive to network latency. For this, you still get performance improvement, but not a whole lot. For buffered networks, so you can apply this throttling to both bufferless and buffered networks. This is just purely buffered networks. And for buffered networks, you of course get less performance benefit because congestion is less of an issue in buffered networks, but you still get some performance benefit, which is not very high. But whenever you need that performance, it may be a good idea. It's consistent across, again, these different workload categories. So one other benefit of this is this actually improves fairness because now applications that actually need to make progress, latency sensitive applications make progress. So fairness is improved by 15%. So this is the fairness measure. Fairness measure is, this is just a foreshadow of one of the lectures next week. Basically, we use maximum slowdown as the fairness measure. Basically, this is we measure the slowdown of each application when it's sharing resources compared to when it's run alone on the system. And we find the maximum of those slowdowns. If that slowdown is high, then we're unfair. If that slowdown is lower, we're more fair. So we reduce that maximum slowdown for both buffered and bufferless networks. And energy efficiency also improves actually because you're not actually, so here, for example, by reducing congestion, you get significant energy improvements because the packets are not circling around again, right? It's about 8.5%. It's higher than the performance improvement. And for buffered networks also, you improve energy efficiency because you don't utilize the buffers unnecessarily. Because once your buffers become full, you have all these acknowledgement traffic that says well, once your flits are occupied in the buffer, actually we do use buffer power optimization techniques also, because once your buffer is not occupied, you can actually turn off some of your buffers, right? By reducing congestion, you can get better performance and also increase the possibility of buffers to be not utilized, which means that you can turn off your buffers. So it's synergistic between performance and efficiency. So there are a bunch of other results in the paper also, and you can take a look at that. Okay. Any questions? There's a lot more work to cover, but I'll stop here, I think. So this is another exciting area. I'll just give you some of the basic ideas. Here, we employ similar mechanisms. This is actually much older work than the previous one, but the idea here was to design a router that prioritizes applications differently. And you can actually, instead of source throttling, I think you need to do all of these in conjunction, and we have mechanisms that do all of these in conjunction. But when you have contention in a router from different applications, which application do you prioritize? Again, you can figure out which applications are more latency sensitive and bandwidth sensitive and rank those different applications based on the benefit they would get from the network, from prioritization, and pick the application that would benefit the most from that prioritization. And this has heuristics as to how you can pick that application in that prioritization. And also you need to, once you start prioritizing applications, you need to ensure that there is no starvation, right? So how do you actually fix the starvation problem? And I've already talked to you about using the concept of slack, figuring out, slack is the notion of how much you can delay a packet without affecting system performance, and you can estimate that and do the prioritization decisions based on slack, and you can combine it with this and you get much better performance if you do that, as well as efficiency. But I'll leave the slides, I think, and you can take a look at the slides and the papers certainly, and I'd be happy to talk about them separately. Yes?
So the number of applications you're having are limited, right? I mean, the big problem that we have in the internet is the number of flows are huge. You don't have the scalability issues, I guess, on the chip.
That's right.
That we have on the internet.
That's right. Yeah.
So you can do it on a per application basis.
That's right, exactly. Exactly. But even then we classify the applications because the router becomes, the critical path increases as you add more priority levels. So we still don't do it the paper discusses what happens if you do it on a per application basis versus if you group some applications and treat them the same. And the final solution is grouping the applications.
It's interesting, a lot of these works as parallels. I mean, first time hearing about on-chip networks, I've been doing the off-chip one.
Oh, you've been doing that part? Yeah, you might be interested in that SIGCOMM paper then, that talks, at least looks at the issue from a congestion and scalability perspective. There are a lot of other interesting comparisons between these two networks, but. Okay, well, thanks for sticking around.